In the clinic, we're seeing these infections with absolutely staggering resistance profiles. It often makes you wonder, how did the bacterial software carrying these genes get so powerful so fast? Well, that brings us to the first critical question we need to answer. How did a small group of basically harmless bacterial plasmids from 100 years ago transform into the multi-drug resistant enemies we face in our hospitals today? And here is the second question. What if the most dangerous vectors out there are actually fusions, like Frankenstein's monsters of the microbial world? The answer to this has direct implications for how we understand the threat we face every single day. To get to the bottom of this, we're going to unpack a really landmark study from 2025 in the journal Science. It's titled Pre- and Post-antibiotic Epoch: The Historical Spread of Antimicrobial Resistance. And, of course, links to the bibliography are in the description below. Okay, so let's get right into it. First up, we have to define our main subject here, the plasmid. So you can think of them as these little interchangeable software cartridges. Bacteria can just swap them back and forth to instantly gain new functions, like, for instance, the ability to completely defeat our best antibiotics. So, to really understand today's super plasmids, we have to see what their ancestors look like. But how in the world can we do that? We do it using a really unique piece of evidence, the Murray collection. You can think of it as a kind of bacterial time capsule, a plasmid fossil record, really, from the pre-antibiotic era. What's so great about this collection is that it allowed researchers to compare these ancestors with their modern-day descendants, and this comparison reveals their incredible evolutionary journey right through the antibiotic age. So what did this comparison, this look into the plasmid fossil record, what did it actually show us? Now, what's really interesting here is that it shows three pretty distinct paths for these plasmids. Let's take a look at the two that really matter for us today. First up, we have the survivors. You can think of them as the original models that have just toughed it out for a century, picking up resistance genes along the way, but, keeping their core structure. But the real villains of our story, they emerged from a totally different evolutionary path. And this chart illustrates the point brilliantly. These fusion plasmids, these Frankenstein's monsters that have been stitched together from the parts of older plasmids, they are significantly larger and they carry a much, much heavier arsenal of resistance genes. So here's the crucial point. These fusion plasmids, while they only make up about 22% of the plasmids that were studied, carry a staggering 50% of all the antimicrobial resistance genes detected. And this connects directly to the patient that's right there in front of us. That pan-resistant Klebsiella is the direct result of this high-risk evolutionary strategy. So, based on all of this, here are three practical points to take away from this research. If you want a simple way to remember this and share it with your team, just think of this phrase: fusion is the superbug's engine. It really captures the core dynamic that's driving the spread of this complex resistance. So this whole investigation into the plasmid past gives us a really clear and, frankly, concerning picture of our present clinical reality. This understanding completely transforms how we view multi-drug resistance. It's not just a list of genes anymore, but the product of a very powerful evolutionary process.
Thank you for your time.